The cold electricity coil of UFOpolitics. A man who uses the forum ID of UFOpolitics has been sharing his insights and experiences on various different forums, such as the one dealing directly with the production and use of cold electricity in solid-state circuits. http://www.energetic-forum.com/renewable-my-motors-my-mode-radiant-my-energy-1.html. His insights are unusual and very important. His basic statement is that if a coil is pulsed, using a circuit like this, then conventional hot electricity pulses the coil when the transistor is switched on, but if that current is switched off rapidly, then there is an inflow of cold electricity into the coil from the surrounding environment. That inflow of energy can be collected and diverted to power a load through the use of two high-speed diodes which can carry considerable current as the power inflow is substantial. The inflow of energy occurs when the transistor is switched off, and so it is desirable to have the transistor switched off for most of the time, in other words, a low percentage duty cycle for the transistor. There must be a significant load on the cold electricity output. If there is not, then the cold electricity will flow back into the hot electricity section of the circuit and it may damage the transistors. Tom Bearden states that resistors boost cold electricity rather than hindering its flow, so the load should be a coil, a DC motor with brushes, or a fluorescent light bulb. It has been observed that the incoming energy tends to flow inwards towards the center of the coil, so an additional method of collecting this extra energy is to place a second coil inside the main coil, and wound in the same direction as it, like this. This provides two separate, independent cold electricity power outputs. Diodes are not needed for the inner secondary coil. This inner coil is a pickup coil and is not related in any way to the number of turns in the hot electricity pulsing coil. Instead, this coil collects inflowing cold electricity during the period when the pulsing coil is switched off. The hot electricity pulsing coil can be wound directly on top of the extra pickup coil, or the extra coil can be wound separately and placed inside the main coil spool. Very surprisingly, it is recommended that the powerful high-speed diode used to channel the cold electricity out of the circuit be followed by a small 1N4148 silicon epitaxial planar high-speed diode, 75V045A, as this is said to clean up the cold electricity output even more. It is important that the cold electricity has to encounter the more powerful silicon diodes before reaching the 1N4148 diodes, so the order of the diodes is very important, and should be as shown here. Alternative diodes for the NTE576, 6A, 35NS, 400V, are the NTE577, 5A, 70NS, 1000V, and the HFA16PB, 16A, 19NS, 600V. The main requirement is high-speed operation, voltage rating of at least 400V and current rating of at least 5 amps. There is one additional thing to be done with this circuit when a DC output is required, and that is to apply filtering to the output. First, when the energy has passed through the NTE576, or equivalent, power diodes, it encounters a high frequency, low capacity, high-quality film capacitor placed across the output in order to siphon off any high-frequency voltage ripple before it is passed through the small 1N4148 diodes and into a smoothing and storage electrolytic capacitor. Storing the cold electricity in the electrolytic capacitor converts it into conventional hot electricity. While this circuit looks like something which you just switch on and it works, that is not the case, as there is an essential start-up procedure where the signal applied to the transistor is started at just a few cycles per second. And 50% duty cycle, and that input is then adjusted carefully and slowly while monitoring the voltages and currents produced by the circuit. This is a seriously powerful system with the capability of producing a major power output. It is very important that the circuit is not powered up without a suitable load on the cold electricity output. A suitable load is a self-ballasted 230-volt fluorescent light. It must be understood that just flipping the power switch to its on position is not sufficient to get an inflow of cold electricity. Instead, it is necessary to progress the startup sequence carefully, and a fluorescent light is particularly helpful for doing this, although a neon bulb is also a popular choice of temporary load, because these devices allow the current flow in the load to be assessed visually. Before switch on, the input oscillator is set to 50% duty cycle and minimum frequency. Then the frequency is raised very slowly, causing the lamp to start flashing. As the frequency is raised, the current drawn from the battery needs to be monitored, as it is the current flowing through the transistor, and the current is kept down by lowering the duty cycle progressively. This process is continued carefully, and if successful, the color of the light produced will initially be purple or green before reaching continuous bright white light. Videos showing the light produced and the fact that it is not dangerous to life or affected by water can be seen at http://www.youtube.com/watch?v=w1kalmgfscg list =UUDMFG5BS0Y North Dakota 2B5ZAZXXNG index =1 feature =PLCP. The driving force is a series of powerful magnetic pulses, and implementing the physical circuit to achieve that requires careful construction. The battery driving the circuit is a 36-volt combination of cells. The coil is wound as an air core construction on a 2-inch, 50 mm, diameter spool, and the DC resistance is arranged to be about 1.4 or 1.5 ohms. This, in turn, requires a substantial drive from the transistor, and so it is normal to connect 6 powerful output transistors in parallel in order to spread the current flow between them, as well as dissipating the heat generated across several transistors bolted to a common heatsink of generous area. How the coil is wound is something to consider. The objective is to have a coil of about 1.5 ohm resistance and which has the maximum magnetic effect for the current passed through it. Copper wire has become very expensive, and so it would be very costly to wind the coil with vast lengths of thick wire, not to mention the very large size and great weight which would be produced by doing that. The copper wire options in Europe are typically to work with half-kilogram reels of wire. The details of some of these are as follows. We can see from this that a 500-gram reel of 14 SWG wire has a total resistance of just 0.09 ohms, and so it would take 16 reels, weighing 8 kilograms and costing a lot of money, to wind just a one-strand coil using that wire, producing a coil which could carry a current of 9.3 amps. As opposed to that, a single reel of 28 SWG could provide 52 separate windings, which when connected in parallel, could carry 15 amps as well as costing and weighing far less. It would be tedious, but not impossible, to wind a 52-strand coil, so a more reasonable number of strands connected in parallel might be used. We are aiming at a DC resistance of about 1.45 ohms in any coil arrangement which we select. The magnetic field produced by a single strand is generally less than the magnetic field produced by 2 strands carrying the same total current. So, if we were to pick 22 SWG wire, then we could measure out 4 133.5 meter lengths, join them at the start, and wind the 4 strands simultaneously, side by side, to form a coil with a DC resistance of 1.45 ohms. It is important that the strands are exactly the same length so that they carry exactly the same current and no one strand gets overloaded with current due to it having a lower resistance than the other strands. It should be realized that as the maximum current which the wire can carry is 4.8 amps and the resistance is only 1.45 ohms, the maximum continuous DC voltage which can be sustained by the coil is only 7 volts, and so as a 36-volt battery is being used, we must adjust the frequency and duty cycle very carefully, especially since we are starting at very low frequencies. If the full battery voltage is applied continuously to the coil, then the coil will be destroyed. Various members of the forum have suggested, built and tested different circuits for feeding a variable frequency variable duty cycle drive signal to the output transistor. However, UFOpolitics recommends a simple 555 timer circuit. If you are not familiar with electronic circuits, then read Chapter 12 which explains them in some detail, including the 555 timer family of circuits. The point stressed by UFOpolitics is that the output taken from pin 3 of the 555 chip passes first through a 100 ohm resistor, and then, every transistor gets a separate feed via a 2 resistor voltage divider pair. The 47K gate to ground resistor is to ensure that the FET turns off properly. It may be possible to increase the value of these resistors, but they should never be less than 47K. The thick lines in this diagram indicate heavy-duty wiring which can carry high currents without generating any real heat when doing so. It is also recommended that although the FET has an internal diode, an extra external high-speed diode, NTE576 or similar, be connected across each FET in order to boost the switching speed. A FET has a gate capacitance of about 1 NF. The faster it can be charged/discharged, the faster the FET will switch, and stay cool. What determines the speed of charge/discharge for the gate capacitance is the length of wire from driver to gate or gates is inductance, where 1 meter of wire produces 0.05 H. In addition to that, different lengths of gate connection wire will create different switching delays, and the different inductances can then initiate high-frequency oscillations with repetitive on/off/on/off switching actions. The result might be burned FETs and lack of cold electricity activities. Another point made by UFOpolitics is that the physical layout should have the connecting wires or tracks kept as short as possible, and he suggests this layout. There are two things to note here. Firstly, the 100 ohm resistor coming from pin 3 of the 555 timer IC is positioned centrally between the 6 FET transistors mounted on the aluminium heatsink, and that point is carried closer to each FET with a low resistance conductor to give a good quality link for the resistors feeding the gate of each FET. Secondly, the heatsink itself is also used to provide a low resistance electrical connection to the coil which the FETs are driving. The connection to the heatsink is via a nut and bolt clamping a solder tag firmly to a cleaned area of the heatsink. Each FET is electrically connected to the heatsink through its mounting tag, which forms its heatsink connection as well as connecting to the drain of the transistor. However, if the aluminium heatsink is a black anodized type, then, apart from cleaning between each FET and the heatsink contact area, it is worth running a thick wire also linking the central FET pins to the output wire connection point. The transistors used in the prototype, and recommended for replications, are the NTE2397. This is not a very common transistor in Europe at this time, and so the popular IRF740 might perhaps be used, as it appears to have all of the main characteristics of the NTE2397 transistor. UFOpolitics suggests the 2SK2837, 500V, 20A, 80A pulsed, or the IRF-P460, 500V, 0.27 ohm, 20A and 80A pulsed. As the 555 timer has a maximum supply voltage of 15 volts, an LM317N voltage stabilizer chip is used to create a 12-volt supply from the 36-volt battery. A 24V battery could be used. The LM317N integrated circuit should be attached to a good heatsink, as it is dropping off 24 of the 36 volts powering the circuit, and so, has to dissipate twice the power that the NE555 chip uses. There are various pulsing circuits which have been used successfully with this system. UFOpolitics considers the NE555 chip to be the most straightforward, so perhaps my suggestion for this arrangement might be a suitable choice. This gives fine control of the frequency and independent adjustment of the mark/space ratio or duty cycle, and it needs only 3 very cheap components other than the controls. If the expensive multi-turn high-quality variable resistors are available, then the 47K fine-tune variable resistor can be omitted, as those variable resistors make the adjustments easier to control. The lin in the diagram stands for linear, which means that the resistance varies steadily at a constant rate as the shaft of the variable resistor is rotated. In the UFOpolitics circuit, it is important to turn the frequency down to its minimum value and set the mark/space ratio to 50%, before powering the circuit down. Otherwise it would be easy to power the circuit up with a much higher frequency than is advisable and so, causing damage to some of the circuit components. There are ways to boost the performance over what has already been described. One way is to insert a stainless steel core inside the coil. Stainless steel is supposed to be non-magnetic, but in practice, that is not always the case. However, ideally, this steel core is improved by altering its crystalline structure by heating it up and then quenching it by submerging it in cold water. Another improvement is to isolate the coil better at switch off through the use of a second transistor. Having a switched off transistor at each end of the coil certainly blocks the flow of hot electricity, but if Tom Bearden is correct, the resistance of the transistors in their off state will actually boost the flow of cold electricity as it reacts in the reverse way to how hot electricity reacts. The arrangement is like this. While this looks like a very simple circuit to implement, that is not the case. The upper transistor is switched on by the voltage difference between its gate G and its source S. But, the voltage at its source is not fixed but varies rapidly due to the changing current in the coil, and that does not help when solid and reliable switching of the upper transistor is needed. A P-channel FET could be used instead, and that would have its source connected to the fixed voltage of the plus of the 36V battery. That would help the switching enormously, but there would still be timing issues between the two transistors switching on and off at exactly the same time. Other circuits have been suggested for doing that type of switching, but in the early stages, UFOpolitics recommends that things be kept as simple as possible, so using just one transistor is the best option. Switching speed is an item of major importance, even to the extent that the reduction in the speed of switching caused by using more than one transistor in parallel has caused the suggestion to be made that it might actually be a better option to use just one FET, since these high-performance FETs are capable of carrying the whole of the switching current, and it is mainly to lower the FET operating temperature that multiple FET use is suggested. Every extra FET used in parallel slows the switching down. However, it should be realized that there is a somewhat greater risk of burning the FET out if just one is used. The coil dimensions recommended are 2-inch, 50 mm, diameter and 2-inch length. The wound coil is likely to be about 3 inches, 75 mm, so making the flange diameter 4 inches, 100 mm, is realistic. The recommended material is fiberglass, which has high heat-resisting properties as well as being easy to work. The personal choice of UFOpolitics is polyester resin with methyl ethyl cathol, MEK, hardener. A suggested alternative is acrylic, which is not as heat-resistant. Acrylic is excellent for high-frequency applications, but the circuitry does not operate at high frequencies. Whatever spool material is chosen, it needs to be non-magnetic. When connected in the circuit, the start of the coil winding wire goes to the battery positive. Here is another coil wound on acrylic tube and with all 4 diodes connected to the ends of the coil. It should be understood that cold electricity provides almost unlimited power, and it has uses which are not readily understood by many people. UFOpolitics suggests that the hot electricity drive circuitry be tested initially using just a resistive load. If everything checks out correctly, then test with a lesser value resistor in series with the coil, and if that checks out satisfactorily, then testing cautiously with the coil on its own. Cold electricity can charge batteries rapidly, and after a series of charge and discharge cycles, batteries become conditioned to cold electricity, and the experiences of Electrodyne Corp staff show that large conditioned batteries which are fully discharged, can be recharged in under 1 minute. A member of the present forum has tried this with the UFOpolitics circuit, and he reports, "Yesterday a friend and I took 6 identical, old, 12V, 115Ah batteries and made 2 36V banks. We set up bank A, the better 3, to power the device to charge bank B. Bank A was 3700V at rest and bank B was 3494V. My lowest frequency was 133 Hz, I need to change my cap and add another 100K pot with the one which is controlling the frequency, and the duty cycle was at 13%. We started at 2A draw on the primary circuit. As I raised the frequency, the batteries on charge jumped up to 38.4V, then dropped evenly to 36.27V and started up again, at about 0.01V every 2 seconds. After 2.5 hours, they were up to 39.94V. At this point we stopped the charging and let everything rest for 10 minutes. So far everything seems very normal for this kind of charging, except that the device appears to be very stable and powerful, pushing the batteries right on up continuously. The primary battery voltage dropped initially to 3620V and stayed there the whole time, then recovered to 3698V during the 10-minute rest. Then we switched battery banks A and B and charged the opposite way for about 20 minutes. We stopped and rested things again, swapped the banks back and started charging bank B again for another 20 minutes and stopped. After letting the batteries rest for a few hours in order to get truer readings, bank A was at 3707V and bank B was at 3832V. Both battery banks had gained power. These were not very good batteries, either. One of the bank B batteries was at 1069V at the start. Another interesting note, the amp draw on the primary dropped from 2A to 15A as the frequency was raised from 133 Hz to about 550 Hz. This was with the very first use of cold electricity with these low-grade batteries, and a major improvement can be expected after many additional charge/discharge cycles. This completely overcomes the factors which make a battery bank unsuitable for household power. If an entire battery bank can be recharged in just minutes, then it opens the way for serious household power using a battery bank. Cold electricity can also run motors very powerfully. Forum member Netica found that putting a capacitor across the motor terminals improved the running very substantially, giving impressive performance. His video of this is at http://www.youtube.com/watch feature =player_detail page &v=7UAYKHRPDPC and the motor, running off an air-carry coil with no steel insert. His setup looks like this. It is also possible to submerge cold electricity circuits in water without causing any harm. A video of this is located here, http://www.youtube.com/watch?v=w1kalmgfscg feature channel list =all including demonstrating the use of very powerful light bulbs. A general running demonstration is here. http://www.youtube.com/watch?v=yvzhkpequgc feature =player_embedded